Okay, let's begin our lecture proper. On last week, we stopped at these slides and we began to talk about operations on discrete sigma. We are interested in the following 6 operations, and the easiest one that you can see is, of course, the multiplication. So let's see what we do for multiplication. In multiplication, we are interested in the signal x of n going into a system, and we basically multiply sometimes you draw it this way, it's easier to see. For example, the coefficients is multiplied by 3, and then y of n will be equals to 3x of n. That's it. So it is simply a multiplier. Of course, the multiplier can be positive numbers or negative numbers. So multiply by negative 3, then we get negative 3 of xn. There are others that are like time delay, and I'm sure you have seen this before. This is an example. The first figure is an example of xn. It is a discrete time, as you see that the x-axis is only the x-axis is important only at integer values of n, and x of n only have values that in these integer values. So in this case, it looks like half a triangle and stops from 0 to 4. In this figure, what we then see is that in a time shift operation of a delay, the whole figure is shifted right-hand side, in this example, by 3 samples. To see that properly, all you need to observe is the first sample x of 0, which now happens at x of 3. The whole signal has been delayed by 3 samples in this example. So we say that in this case, here, this is x of n, and here, for example, this is y of n equals to x of n minus 3. So what do we put in this block? Okay. Now, typically, we'll draw it this way. X of n, z minus 1. This guy will be x of n minus 1. We pass again through z minus 1. Here will be x of n minus 2. And we pass again a block called z minus 1. And now we have x of n minus 3. So now you realize that this block shows a delay by a single sample operation, which is what we want here, z minus 3. So we have 3 blocks in series. Of course, you could have just simply say z minus 3, and then it will be the same. The third figure here is called time advance. If you compare time delay and time advance, the operation is simply shifting the other side, increasing by time. So what do we mean by advancing in time? In here, the original data is happening at x of 0. In here, the data is observed at x minus 2 before it happened. Okay, so this is what we are talking about. X of n is occurring at, is having values of 0 at n equals to minus 1. At n equals to 0, it has some values here. And at n equals to 1, it has some values here. And so on. Y of n is a sequence of x of not n minus 2 now. In this example, is n plus 2. So what does it mean? It means that at time n equals to minus 3, n equals to minus 2, n equals to minus 1, at n equals to minus 3, we are using y of minus 3 is equals to x of minus 3 plus 2, which is equals to x of minus 1. So this value is this value here. Y of minus 2 is therefore x equals to 0. This value is this value here, and I now should draw with your value a here. So what it means is that y of n at time before x has happened can observe x. That's what it means. So we are seeing the future values of x with respect to the time n. Alright. Now this is a bit strange for some of you all. After a while you get to figure it out. In real examples, we're always observing, future values. Sorry, we're not observing future values. We're always observing past values. So delay is a very natural operation, not advanced. But in DSP, if the sequence of data is available to you, it doesn't matter whether you're seeing the past value or the future value, because the sequence of numbers is already available. In this last example, it is called joint time scaling and delay. In this example, what we are doing is this. Y of n is equals to x of a n minus d. So we are performing some delay and some operation of scaling or reflection. For example, my example is x of minus n minus 1. So I'm performing, in this example, it's not scaling. A is 1, so it is not making n bigger or smaller. It is simply a reflection. And here I'm delaying by 1 sample. In the figure, you see this figure here. This is a mirror image of this original figure, but shifted. So it will trick many students whenever I write such an equation and I ask you to draw the resultant sequence. To understand what's happening, please observe these two equations. So what are we going to do here? Y of n is equals to x of a n minus, in here I write b. A and b are integers, so is n integer, because we are in discrete time. Now let's play and set n equals to 0. Therefore, y of 0 is simply x of a times 0 minus b, and therefore now we get x of minus b. So this equation must satisfy. And in the other equation, I'm going to set a n equals to b somehow. And if this is true, then what I will get is, implying n equals to b over a, I will get y of 0 is equals to x of a times b over a minus, sorry, I made a mistake. It's b over a, right? B over a equals to yes. So simply it is just substituting these two equations of these values of n equals to 0 and n equals to b to a to get these two expressions. And these two expressions must agree. And for these two expressions to agree, you will realize that you have to do it in this order. If you have a joint operation of delay and scaling, you must try to do, or not try, must try, you must do time shifting first, followed by time scaling. If you follow this rule, these two conditions will satisfy and you'll get the diagram over here. Alright. Now, one last example. In this example, it is x of t, which is continuous time, and I get this square block from -2 to 0, and I get this funny looking block from 0 to 4 over here. And in this example, I'm going to say y of t, which is this resultant signal, is x of 2t. I'm now scaling time. In this example, y of t has 2 times faster time than x of t. When things are 2 times faster, time compresses over here. So imagine if I'm looking at time index is 2, and since it is 2 times, this y of t is 2, t equals to 2, therefore x is 2 times 2 is 4. So this point over here is this point over here. You figure out now that in this example, when the coefficients multiplying by the time is greater than 1, we are compressing. If the coefficients is less than 1, we are expanding. Okay, so this is the time scaling example. We are not always compressing depending on the value of the coefficients multiplying by time. Now, this is the joint operations we are talking about. Again, we have y of t equals to x of 3 times t minus 5. And if you are new to this, you will be wondering whether you want to do delay first or scaling first. And if you attend this, you will know that we are going to shift first, delay, and then we are going to time scale. So let's try. First, we delay by 5 samples in continuous time. So this whole thing is shifted right because it's delayed. So we are now in this figure here. The red dash is the original figure. The blue solid one is the new position of the figure. How do we check? We check the first position. Now it's at t equals to 3. Original position was t equals to -2. So we know that we have just shifted right by 5 samples, or in this case, 5 unit time in continuous time. Now, what about 3t? Remember that we are multiplying coefficients larger than 1. Time is now compressed, and we basically have forced this figure to be 1/3 the size now. And how do I know it is 1/3 the size? Well, look at time at 3. If time is compressed by 1 into 1/3 of the original time, it becomes at index 1. And the other figure is at 9. It now compressed to 3. So the whole figure is compressed.